Good morning. This is Mr. Weiss with an 8th grade video for, starting to learn the periodic table. And I'm going to see if some people show up here. I hope they do. If you are here, say hello so I know who's there. And I'm trying to get this situated so you can see the whiteboard behind me. That's where we're going to draw things and learn about stuff this morning. And I'll give folks a couple minutes to arrive, and I'm going to write down who's here. If you can't comment, you may have to use a different email address. That's my AP kid said yesterday. So see if you can comment. About half of them could comment. But if you use a non-school AP address, then I think you'll be able to comment. At any rate, comments would be good because I have lots of questions I want to ask you. We'll review, and then once we review, we'll start going into some new stuff with the periodic table. So that's kind of our goal for today. I think you have one. I sent you one again, a digital one, but you, I think, have the paper one, I hope, at home too. That would be good. Okay, so I'm going to go ahead and begin. I only got a couple of you, it looks like, out there, and no one's commenting yet. If you can, say hello so I know who's there. But I will just begin. So it's been a while, and I'll just say I enjoyed your 8th grade group. I enjoyed skiing and singing and hiking with a lot of you. And I have corona, although I feel okay. And a lot of you do as well, I know. So we're home this week. That's the way it is. Okay, let's review some atomic models. That's kind of where we were once we left each other before the ski trip. So here we go. Atomic models. And you can look in your notes if you want. Hey, there's one person. Hello, Helen. Glad you're with me. Okay, let's see if a couple more can chime in and say hello as well. Atomic models. What I mean is what people believed that the atom looked like. And the easiest one we had was, and there's Lord Kiwi. Hey, you want to tell me who you are? That would be great. I doubt that's your real name. So here we go. The Dalton model. Dalton, called the father of chemistry, had this really simple model. Remember, he just said, there's an atom. It's a sphere. We don't know much about it. And we don't know what's in it. Julian. Okay. All right. And Julian, it was good skiing with you. Helen, it was good singing with you. Next model was the Thomson model. So this had a little more to it because they realized with Thomson's model that there was positives and negatives in an atom. And they didn't know how they were arranged, so they just sort of put them in here randomly like that, okay? Called the plum pudding model. Next model was the Rutherford model, and I'm going to pause with that. Ernest Rutherford. And the Rutherford model was the one that had, the first time had this thing in the middle of nucleus. And by the way, I'm going to ask you guys questions, but I'd love to see a few more people there. So I got 2 people. If others could say hello, great. If you can comment, do, because I know it's possible. I've turned that on, but you may have to have a non-JKFS email address. All right. So the Rutherford model had this thing in the center, which he called a nucleus. Comes from biology, the nucleus of a cell, even though this nucleus is a lot smaller. And on the outside, of course, some electrons, okay? That was the Rutherford model. And the Rutherford model came from the gold foil experiment. I don't think we finished that before the trip, so I want to sketch that one more time because it's probably the most important experiment that was done to tell us what an atom is like today. All right, so let me erase these first two models and sketch a little bit of the gold foil experiment. Unfortunately, I don't have any gold color, but that's the way it goes. So we're going to just say, okay, here's some particles coming out, and they were shot at a piece of gold foil. So here's the gold foil. And these little tiny particles were called alpha particles. You'll learn about those in ninth grade. They're small alpha particles. And around this whole gold foil experiment was a detector. And this is what Rutherford thought. He thought the little alpha particles would just go through and maybe like get deflected or repelled or attracted a little bit so that they'd land out here like so. And most of them did that. Most of them went straight through. But once in a while, bang, one would land out here, bang, or out here, or out here, bang. Not a lot, but once in a while. So again, this was the gold foil experiment. So Rutherford said two things. So he didn't just have this model, but he kind of came to two conclusions about atoms. And he said, hey, because most of the alpha particles are landing right here, that therefore most of the gold foil, here's the gold foil. Not gold foil. Okay, back up, kid. Okay, so he said, hey, because most of the alpha particles go right through the gold foil, that must mean that most of an atom is empty space. In fact, it's like 99% of an atom is empty space. So most of atom is nothing. Nothing is empty space. And that's because of this right here, okay? So, but, and here's the big but, every once in a while, and now we're talking about these spots here, okay? Bing, 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 bing. Every once in a while, the alpha particles must have hit something really hard and really small because most of them are going through, but if they hit this hard thing, they bounce back. And that hard thing is what he called the what? So once in a while, an alpha particle hit a small, massive thing. Massive meaning that's where the mass is. And it's the massive part of an atom called the Either of you got it? Helen or Julian? What's that part called? What am I talking about? Just so I know you're following. Yes, I know you're eating your cereal and hanging out too. By the way, we should probably take notes on this, especially when I get to more of the new stuff. See if either of you can type that in. So what did I hit here in the atoms of gold that must have then bounced off and gone in weird directions? Well, no answer. Then I'll just write the nucleus. So that's why Rutherford's model has a nucleus in the center. It's really small, and the atoms are around it. Thank you, Julian. Okay. Hey, both of you had it. I think I have a lag in time from when you answer to when I actually see it, but you both got it. Thank you, Julian. Thank you, Helen. Okay, I want to give you a size comparison, and I don't know if we did this, okay? So the size comparison goes like this. If either of you have been out to the Olympic Stadium from 1936, the Olympics, it's big. And in that Olympic Stadium, if I had a soccer ball in the middle, right here, Olympic Stadium. If I had a soccer ball, and I know that'd be too big really, but I can't draw it any smaller. So football. That's about the same scale as an atom. Here's what I mean. So most of an atom would be the Olympic Stadium. And the soccer ball would be the nucleus. That's how tiny the nucleus is. And all of the Olympic Stadium. So if an atom was as big as the Olympic Stadium, most of the Olympic Stadium, like most of the atom, would be nothing. Nothing there. Okay? Only the only soccer balls in the middle, and that would be the nucleus. And that would be roughly the same size as the actual nucleus is in an actual atom. And as you know, because we've had this in our last quiz, the electrons are even smaller. They're just 1/2000th of the size of a single proton or neutron. So somewhere flying around here are the electrons, but they're really, really puny. Okay? They're really, really, really small. So I want you to know that most of an atom is empty space. And that's weird because atoms make up everything. This doorknob, this door, this whiteboard, me. So most of what we are is nothing. So you're made mostly of nothing. Sorry to tell you that. 99% of what you are is nothing. Why? Because we're made of atoms, and atoms are mostly nothing. A lot of empty space in atoms. It's weird. The nucleus is super, super, super small compared to the size of the atom. And atoms are small anyway, right? So now we're talking about something that's really, really, really tiny. So I did that to give you an idea of the relative size of parts of an atom. So an atom's small, but boy, the nucleus is pathetically small, like the soccer ball in the Olympic Stadium. So this whole thing, just to make it clear, would be the atom. And the soccer ball would be like the nucleus. Puny. We can't draw it that way, and we don't, because you and I got into the next model, which is called the Bohr model. And we're going to now review that a little bit. You might say, Mr. Weiss, this is all review. Yeah, don't worry, we're getting to new stuff. But it's been several weeks. That's why I'm reviewing with you. I find that in the 8th grade, it's super important you guys have a really solid foundation. I want you to really understand what atoms are made of and what people think they look like. So far we got this model, Rutherford model, electrons around there, nucleus in the center. Okay, So you can always stop the, I'll send you the video later so you'll have this if you didn't get it all written down. So what happened then? Well, you and I had what's called the Bohr model. And the Bohr model had the nucleus in the center and these what are called energy levels. And we know that, right here, nucleus. So that's like the Rutherford model. But the electrons had a cool pattern. I'll just put a couple here. And we'll put them all. So the Bohr model is nucleus in center, still, and energy levels containing electrons. Now, again, I gotta draw on a two-dimensional surface, but it's 3D. Like some of the folks on, in the last quiz or our discussion talked about circles of electrons. Well, they're not circles, actually, they're spheres. Or really the best way to say it is that these suckers are in energy levels, okay? And got a question from Julian. Okay, so Julian asked, is the empty space in an atom a void, like in space, or is it actually just nothing? Well, those are the same thing, as it turns out. Most of outer space is a void, which means there's no atoms in it. Like if I took a cubic meter of outer space, there might be a few atoms in it, but not much. There's a lot of nothing in outer space. And if I took a single atom between the nucleus and the electrons, there's nothing also. So whether it's in outer space, Julian, or whether it's in the middle of an atom, it's still nothing. So no matter. You might say, well, can't like air get in there? Well, no, air is made of atoms, so you got to get smaller, okay, to a single atom. And if I got just a nucleus and electrons, turns out most of it is empty space. And in outer space, like between the planets, between the Earth and Mars and Earth and the Sun, most of that is also containing nothing, very few atoms or molecules in outer space. Very, very few. That's why if I have a spacecraft and I push it, right, back to physics, if I push a spacecraft to give it some force, it'll keep going because it's not going to have a lot of air friction because there's no air out there. There's nothing in its way except a very, very few amount of atoms. So if I push something in outer space and it's not near a planet, that sucker will just go and go and go forever. And that's why. Not hitting much of anything out there. All right, it's kind of cold in my basement. I've got to blow my nose. Hold on a second. Good question, Julian. All right. Any other questions from folks? Just type in. I see I got like 7 of you now. It's too bad you guys can't comment, but that's life. I know some of my AP kids had a problem commenting until they went and used a non-school email address. So maybe try that next time. Where are we at? The Bohr model. Okay, so how did Niels Bohr come up with this idea? This is where we've got something new to talk about. Hey, there's another one. Good. Okay, welcome, Reese. I think I got to ski with Reese too. So, how did Niels Bohr come up with this idea? You might remember too that he came up with a particular set of energy levels, and he said this, that energy levels contain Whoops. Oh, if I could spell that, I'm sorry. I'm too busy thinking about the next thing. Contain 2 electrons, then 8 electrons, then 8 electrons, and that's as far as we go in this course. So the energy levels have a certain number of electrons. And how did he come up with this idea that there's levels or energy levels of electrons? Okay, here's what's going on. The whole thing has to do with light. So I'm going to raise this because I need a little space right here. And I'm going to draw a new atom. And here's more or less what scientists think is going on. You ready? This is pretty wacky, so pay attention. It's also the same reason you got light on probably over your head right now. Ready? So here's the nucleus. Let's just draw a single energy level with 1 electron. Maybe I'll make that red, just for grins, okay? There's my electron. Here's what Bohr. I don't want to say he discovered it, but here's what he thought was going on, okay? And this is why he had his model. Bohr said, hey, what I think is happening is if I give some energy to the electron, and like you and I did last semester with electricity, so I give it a little jazz, I give it a little energy, the electron gets excited and it jumps to the next higher energy level. I'm going to show that jump right now. So let's say the next energy level is empty, and the electron goes, woo, somebody gave me some energy. Watch this. Whoa. And now my electron is up here. Well, where the electron came from is called the ground state. Just like you and I stand on the ground, an electron where it begins is also called the ground state. So let's say for this electron, it's right there at that energy level. And then if I jazz it up and give it some energy, then it's excited, and we call it the excited state. And that's where our electron is right now. Okay, now here's the rub. In other words, here's the interesting thing that happens. When an electron is in an excited state, generally it doesn't want to stay there. Just like if I throw this up, it doesn't stay there, it comes back down because it goes to like a lower potential energy. We learned about potential energy last semester, right? So it goes from a high potential energy to a low. Well, that's what an electron does. It doesn't stay up there, it comes back down. But when it comes back down to the ground state, it gives off that extra energy on the way down, and it gives it off as light. So I'm going to show that with some little green magic marker. And I'm going to write about that over at the side, okay? That's really important. And that's why Bohr thought there were different energy levels, because he could jazz up any electrons in any element and make the electrons give off light. And to give off light, his theory, which looks like it's a pretty good theory, by the way, his theory is that the electrons get jazzed up when I give them energy. They don't do it on their own. I got to give them electricity, usually, just like your electric light over your head. It's getting electricity. It jazzes the electrons up, and on the way back down, they give off some kind of color of light, white, blue, red, whatever. Here I wrote some little green marks, but it could be any color depending on the jump. We'll talk more about that later. So Bohr said that electrons can be, I'm going to use now the scientific word, energized. Electrons can be energized to leave their ground state right? Like we talked about standing on the ground. Electrons can be energized to leave their ground state. Oh, that's a terrible S. And go to an excited state. When they drop back down, they give off light. That's how we get light. That's how you guys get electric light to see by, right? So that's kind of a big deal. So when the electron drops back to the ground state, let's say the extra energy, that's really what's happening. The extra energy is given off. I'm almost done. As light. And I'm finally done. Let me read that to you and make sure if you have questions, you can ask me too. So Bohr said that electrons can be energized. So they're in what he called energy levels, and the lowest one's called the ground state. So they can leave their ground state and go to an excited state. So I jazz them up with like electricity. Then when they drop back down to their ground state, because things tend to go back down to where they were if I let it drop, right? They give off the extra energy as light, and you and I see that light. Now, with one electron, it's not a lot of light, but if I jazz up a whole lot of electrons, like in a light bulb, like I have over my head right now, it's enough light to see by. But we're talking about millions and gazillions and quantrillions or whatever of electrons. We're talking about lots of electrons moving to outer energy levels to excited state and dropping back to their ground state. And they're not all doing it at the same time. So when you and I see the light, it looks constant because there's so many electrons all the time doing this changing back and forth, giving off, and basically changing what? Electricity to visual light. That's what we're doing, right? We talked last semester about energy transformation. This is another one. So essentially, electricity changes to visible light when we jazz up the electron. And it doesn't have to be electricity. It could be sun. The sun does this too, okay? It could be heat. I could give a lot of heat and do this. And turns out that heat is going to be a lab we're going to do when I come back and when you come back. And it's going to involve a Bunsen burner. If I heat up some chemicals, they give off light because we're jazzing up the electrons. I like that way of saying it. I jazz them up with heat and then they give off light as they come back down. Now, that's a lot to throw at you, I know. Turns out every single atom gives off different colors. Every single atom. That's how Bohr included in his model this idea, okay, that every single element, every single different element that has a different sort of atom has its own unique thing. It's like you and I have a fingerprint, right? And no two fingerprints are the same. They're all very unique. No two atoms are the same either if they're from different elements. I should say that. No elements are the same. And they're all different. They all have a different like type of light that's given off when the electrons jump back and forth. What does this have to do with the periodic table? You're going to find out soon. Okay? We're getting there, people. We're getting there. Just like skiing. Sometimes it takes a while to find our way. Okay, so this is called a line spectrum. That's the scientific word. Let me tell you what I'm talking about. And it's again from the ideas of Niels Bohr. And Bohr said that turns out every element when we energize its electrons, gives off a unique set of colors. And the set of colors is called the line spectrum. Let me reread that. Every element, when we energize its electrons, gives off a unique set of colors, the line spectrum, that is like a fingerprint for each element. Now, you might say, Mr. Weiss, this is really like in the clouds. How do I understand this? Well, I'm going to tell you a little story that happened to me that might help you appreciate this, okay? So, my example to help us think about this was a rock. You ready? But this rock was made of metal. This rock was brought in by one of my students when I was in graduate school. So I was doing my master's and I had some students that were undergraduates. And I had a guy bring in a really big chunk of rock, about like this, and it was silver. It was a big metal chunk. Well, we broke off a little piece of it and we tested it. How did we test it? Well, we got its line spectrum. Okay. I used a machine that was able to zap the atoms with electricity and then measure the lines of light that came off as the electrons went back to their little ground states, just like we we're talking about. Okay? So I matched it up and here it is. I got to find the number and I'm going to call it out to you. Oh, where did that element go? There it is. It's element number 83. So if you want to look at your periodic table, you can see what I found for this student, 83. So it was element number 83, which is called bismuth, Bi. Bismuth. And bismuth turned out to be kind of an expensive element. Today it's probably worth even more, but at that time, about 100 years ago when I was in graduate school, at that time, the whole chunk he had was probably worth $200 to $300. Now I bet it's immensely expensive. Okay. Interestingly enough, the chunk of rock he got from his grandfather who died and left him this chunk of rock, but the grandfather never told him where he found it. It's too bad. If he could have figured out where to find more rocks like that, let me tell you, that would have been a mine worth millions and millions of dollars. But he did have this one beautiful sample of bismuth. And bismuth doesn't usually come in big chunks of solid bismuth. It was pretty cool. But, that's the way it goes. He didn't find the mine, so he couldn't go into bismuth. Sorry, bad joke. But true story. True story. He was really happy to find out what the thing was anyway. And he gave me a little piece of it that I have somewhere. Yeah. So what I'm saying is you can actually use this quality of elements to figure out what they are. Every single element, you know. If I had enough of them, I could figure out from atoms of what we're made of, or this eraser, or the board, or the metal here in the handle. All of those, I could zap them with electricity, and yeah, do that. Okay. I'm glad you appreciate the bad joke. All right. Thanks. Nice to know somebody's listening out there, sitting here in my basement. Okay. Okay. So I think we're ready to really start with the periodic table now. Okay. You'll see why I had to do this with you. The periodic table uses this idea of the line spectrum. It's how the thing is really organized. Okay. We're going to look at that in just a minute. All right. So here we go. So what's up with this periodic table? The one we got today is one that was mainly figured out by a Russian guy, and it was like in the 1800s, so not the Russia of today, but the Russia of like the czars and all of that long ago. And his name was Mendeleev. So we use a really modern version of a periodic table like the kind Mendeleev figured out. I'm going to write his name. Mendeleev. That's how you spell it. We're talking like the 1800s. It wasn't the only periodic table, but it's the best one that was around. I'll say first good periodic table. He didn't have all the elements that you and I had. He had just maybe 20 or 30 elements, I think. So he had mainly some here and some here. Today we've added lots and lots to Mendeleev's periodic table. Okay, so now it's really big. And that's about as big as it's going to get, to be honest. We've got most of the elements, other than really crazy big ones that are artificial. But the natural ones are pretty much down here. Natural goes all the way to like 92 uranium. Beyond that, it's kind of all human made, if you know what I mean. So let's see what's going on with the periodic table. Okay? The periodic table has two parts. I'm going to just sort of sketch one here. Okay? So something like that. All right. So the ones that go across here like this, these are called periods. There's a period. Sometimes they go all the way across. That's a period. And if you look at the periods, folks, let's start at number 19. Okay? Potassium, K. If I go across, they increase, don't they? 20, 21, 20. And you know that's the number of protons, right? So that's like the identity of what the element is. I know this is review for you. So we go across a period and we add more and more protons, and I get bigger and bigger atoms gradually as you go across until I get to the end here. We'll see what happens out there. Well, then I just start again. Hey, look at this, 36 and 37's right down there. I think you can see that if you look at your periodic table or the digital one that I sent you. So periods really are just going across, and they gradually increase in size because I add more and more protons and, of course, more neutrons and electrons too. Okay. So periods go sideways, okay? But then I got things that go up and down. And the up and down things These are called groups. Sometimes I've taught this class and we've called these groups families because they have a lot in common. So periods, just to kind of recap here, let's keep the same color. Periods. Whoa, that's not a good way to spell period. I'm missing my O and whoa. Okay, so periods go across and increase as I go this way in number of protons. And I'll write and so on. And you know, electrons and neutrons probably too. But the protons go really regularly. 25, 26, 27, 28, blah, blah, blah. All right. The groups go down and increase. Whoa. How? Let's look at this. I want you to really look at your periodic table. So turn me off for a second if you don't have one and find the digital one that I sent you, because it's essential you're looking at this while I'm talking. Everybody find H, find hydrogen, element number 1. Okay. Go down. You get to what number? 3. What's 3 minus 1? 2. Go down below 3. So we go from H to Li, lithium. We go to the next one, which is sodium, right? Na, or natrium in German. And that's number 11. Well, what's 11 minus 3? 8. Okay, go down one more and you got potassium. All right. Potassium's number 19. What's 19 minus 11? 8. So think of what that means. 1 to 3 is 2. 3 to 11 is 8. 11 to 19 is 8. Do you remember that 288 thing? Wasn't that what we did with the Bohr model and electrons? Go to the next column over. Look at this. 4, beryllium, find Be, number 4. Go down. Magnesium, it's number 12. Oh, 12 minus 4 is 8 again. Go below that, 20. Calcium, Ca, 20 minus 12 is, it's 8 again. We keep getting the same numbers. Well, let's jump over and do somewhere else. Let's go to the very end, the last column. Find helium, number 2, everybody. I think that was somebody's element. And helium is 2. Go down to the next one, 10. 10 minus 2, 8. Next one down, 18. 18 minus 10, 8. 288. We're getting the same darn pattern. Well, that's crazy. That's crazy. What about here? Let's try like a random one. Let's try carbon. Carbon number 6. Go down. 14. 14 minus 6 is 8. Now you might notice I'm not going further down. Why am I not going further down? Because the energy levels get bigger, and that's beyond what we learned in 8th grade. So the bigger elements, their energy levels, I'm not worried about with you. But if we have this idea of 288, remember what that is? 2 electrons, 8, and 8 more. So 3 energy levels. What I'm trying to tell you is we find that pattern all over the periodic table, 288, 288. Or if we don't find the 2, we at least find the 88. Like let's look at oxygen, right? Oxygen, go down 1, 8 plus 8 is 16. So I got the same pattern there. It's crazy. It's crazy. Let's go to scandium, right? No, let's not go to scandium. Yeah, then it gets too big. Yeah, anyway, you get the idea, right? So up to a certain point, the the groups go down and increase with energy levels. So going across, the periods increase with number of protons, but going down, the groups increase with, I'll say, electrons in energy levels. So what I'm trying to tell you is the periodic table, folks, even though Mendeleev didn't know this, is totally based on the Bohr model. It's extremely organized. If you like math, and I know some of you do, the periodic table is very mathematical. In fact, there's a fun little exercise we can do with some of the numbers. Maybe we'll do that when I come back. But it's really mathematical, right? Okay. Let's take our remaining time today and talk about one of the families, okay? Sorry, one of the, I sometimes call them families, but the real name is groups. So I want to talk about one of the groups with you. And the one I want to talk about is the last group, way out here. And I'm gonna erase the board in a second, but I want to go to this group. Can everybody find that last one out here? It has some elements in there I think you know. Yeah, it is cool. So helium, neon, argon, krypton. Don't you like krypton? It's like sounds like Superman. Xenon, radon. I want to look at that family with you. So here we go. I'm going to erase the board and start to talk about this first group with you. So groups. And I'll just say like families. On the ski trip, I had some students in my room, and a lot of them looked like their brother or sister, so I could recognize them because not always, but sometimes families have some resemblance. You know what I mean? It's the same with groups. Some groups have some things in common, they resemble each other in a way. Let's look at this last group. So, this last group contains helium, He, neon. I'm just going to put the symbols, okay? You know what most of these are. Ar, argon. You guys did good on the last quiz, so I know you know a lot of the symbols. Krypton, xenon, and radon. And these are called the noble gases. Kind of a funny name. Sometimes they're called the inert gases. We'll see why that is. And sometimes in German, they're called the Edelgasen. Edelgasen. All right, all one word, as German so often does. Let's see, Reese has, I think, a suggestion for us. Let me see what he says here. There's a cool show on Disney, Disney Plus, narrated by Neil deGrasse. Oh, he's good. I know him. Neil deGrasse Tyson, that talks about a lot about this stuff, and it's really cool. Cosmos. Cosmos. I've heard of that, Reese. So, folks, if you want to learn more about it, maybe Google Cosmos and that show that Reese has put in the chat. Thank you, Reese. Yeah, it is pretty cool. It is pretty cool. So, again, we're talking about this column right out here, this group. And let's see what's going on. Why are they so special? Why are they similar to each other? Well, I'm going to just take an example of one. Let's take argon. Ready? So here we go, Ar. So here's its little nucleus. We're going to do a Bohr model. And it's got 18 electrons. Remember how to do this? Got 18 protons and some neutrons. I don't care how many, but it's got 18 electrons. So we're going to put 2 electrons here in the first energy level. I'm going to put 8 here. And, 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 am I done? 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to put 8 more. Holy moly. So 2 plus 8 is 10, plus another 8 is 18. Yeah, so I need 8 more. 1, 2, 3, 4, 5, 6, 7, 8. Well, notice that every energy level is full. Remember this? If it has 2, the first energy level is full, 2 electrons. The next one is 8, that's full. The next one is 8, that's full. So it turns out argon has completely full energy levels. Well, all of them do in that group. Think about it. In your head, draw helium. Helium's got 2 electrons. It's got a full energy level, done. Neon has 2 energy levels. 2 in the first, 8 in the next. It's full, it's done. Hey, this whole group, the noble gases, what they have in common is they have full energy levels, full of electrons, okay? That's the key to everything. Full energy levels. Well, here's the key to 8th grade and some of 9th grade chemistry. You ready? Everybody wants to be like a noble gas. Well, maybe not you and I, but every atom tends to be like this in one way. Atoms tend to do things to get a full shell of electrons, a full energy level, either to get 2, 10, or 18. But the noble gases already got one. So noble gases don't do anything. So they're very unreactive, or another word for unreactive is inert. And so they're called noble because they don't react with anybody. Oh, I'm too noble to react with you. Why? Because they already have the number of electrons that is most stable. I won't say they want this because they're not like little people. They're just atoms. But to be really stable, you have full shells. We'll see why that is later on. But so let's just say these noble gases are really stable. Noble gases are stable and they don't react with others. So they're very unreactive, if you want to say it that way. Unreactive. Or you can think of it like people. They don't play with others. No, they just hang out alone because they're already full. They have full shells, full energy levels. They don't have to do anything. They don't have to like say, hey, can you give me an extra electron? Or if they got too many, well, would you like an extra electron? I'd like to get rid of one. No. They stay the way they are. And they're called noble because of that. They don't play with others. They don't react with others. Turns out, my AP kids found out that there are a few that do make reactions, but it's rare. For the most part, they don't do anything. Okay? Notice that they're all also gases. So they're all gases. And what that means is the temperature at which you boil them or melt them is really low. Because think of like if I boil water at 100 degrees, then it becomes a gas. But these are already gases. So it turns out their boiling points are really low and their melting points are even lower. So all gases all have low melting points, or if you want to call it the melting temperature, if you like that better. melting temperature, and boiling temperatures. Maybe I should say temps. So all have low melting temps and boiling temps. So they're all gases. What that means, and you'll learn more about this in 10th grade, is they don't attract each other. So let's say you and the person next to you are atoms. Well, like for this aluminum, they're really attracted, so they make a solid at room temperature. Metal atoms bond. We'll learn about that in 9th grade. They bond with each other to make a solid. Gases don't. They don't care about the next atom. Why don't these noble gases care about the next atom? Because they've already got the right number of electrons. Their shells are already full. Their energy levels are already full. So the gases, these are all gases, the noble gases. They have low melting and boiling points because they do not bond even with others of their own kind. They like being alone. Do not bond with other atoms of their own kind. So, first off, they don't play with others. Second, they don't even play with like their brother or sister. You know what I'm saying? Not their brother or sister. They're like their other part. I don't know how to say that. In other words, these are like this. There's one, there's one, there's one, there's one. They're totally separate, okay? These little atoms don't really interact with each other. They just sort of bounce around and are gas molecules. Remember, in physics, I made you guys bounce around the room and pretend you were gas molecules. That's what these do all the time. And they don't attract each other. Why? Because their shells are full. They don't need each other. They don't have to do anything to get a full energy level. They've already got it. I know I've said that about 10 times because it's really important. So let's review here. The noble gases, they're called noble because they don't react with others, like noble royalty or something, like queens or kings. Inert is another word which means not reactive. They don't react with others. Edelgassen, again, edel, right, the Adlige, the royal peoples would not react with others. And there's their members. We got full energy levels. They're very stable and unreactive. They're all have very low melting and boiling points. That's why they're gases. Okay, what do you do with these? I'm going to leave the names on the board and erase around it here because there's a cool use you might know. Especially these four: neon. See if somebody knows. What's neon used for, or argon, or krypton, or xenon? These have a cool use. Well, these four, and maybe someone's typed in, but hey, Reese has got it. You're quick, Reese. And I saw your response quick, which was nice too. Exactly. They're used in lighting, especially in science. Right, Reese? Advertising lighting. You've heard of the neon lights are bright on Broadway? Well, neon lights are filled with neon. That's what makes them red. If you've ever seen red, like advertisements and lights, if you've seen like greenish, it's like krypton. If you've seen, I want to say, bluish is xenon. So you can put in different gases and even mix them to get different colors because we're zapping the electrons with electricity and making the electrons do what? Go out to an excited state and then drop back down. So imagine I make an argon and I make one of the electrons go out here. Whoop, it's in an excited state, and then it drops back. Remember, then it gives off the extra light. Uh, and these are very colorful. These four are used in advertising signs. I'll just say that. And I bet you've heard of neon lights. Well, they're really filled with neon. I'm not making it up. Okay. A friend of mine, she dated a fella in Montana, and he had his own studio. And Kate is here. Good, good. Welcome, Kate. Um, this fellow in Montana had his own studio where he would blow glass, right? Long things of glass, make it into like sign, like Joe's Bar or something or other. And he would then fill it. He had four gases: neon, argon, krypton. Depending what color they wanted, he would like fill it with that gas. Like, let's say they wanted red, he'd fill it with neon. Okay, so I have a nice red flashing sign. So used in advertising signs, that's a really common use. And I'll just say example, neon lights. So anytime you see fancy advertising signs or see pictures in like, I don't know, the Times Square or something like that, you're looking at neon lights. Good. That's a pretty good introduction to noble gases and the periodic table. We're going to do more families when I meet you again. I may do some small written assignment, or I might have a video I'll have you watch, but I'll tell you on Google Classroom. So I hope you all remain healthy, and I'm pretty healthy, a little sleepy sometimes, but that's about it. And I won't see you till probably next Monday or Tuesday, whenever I see you in school. So have a good week. I may do another one of these sessions with you this week, or I might just send you a video of me or someone else talking about the periodic table. Okay, thanks everybody for being here. I appreciate it very much. For those that couldn't make it, if they were sick or something, let them know I will save this video and put it on the stream in Google Classroom so they can watch it. Okay, bye. Have a good day.